I have considered boost converter to show how to measure switch losses in LTspice simulation. A basic knowledge in LTspice simulation is sufficient to follow this presentation. Let me start with a quick recap of boost converter operation. First, I am identifying the components: the input, DC source, an inductor, a switch, here it is MOSFET, a diode, the output side, a capacitor, and I have considered resistive load here. The MOSFET is switched with a fixed duty cycle and a fixed frequency pulses. When the MOSFET is on, the input voltage appear across the inductor and the inductor current increases. At the same time, the output voltage appear across the diode, positive beam on the cathode side, which is reverse biased. So during this on interval, the capacitor provides the current to the load. The capacitor is selected to be sufficiently large to keep the voltage stiff. When the MOSFET is turned off, the inductor current has to maintain continuity, so it flows through the diode to the output. During this time, the inductor current falls to produce the voltage of this polarity. With input voltage plus inductor voltage, the total voltage will be more than the output voltage, so that the diode is forward biased. So during on time, the energy is stored in the inductor. During off time, the inductor energy is transferred to the load. I run the simulation and the waveforms are shown here. The topmost is the gate source voltage of the MOSFET VGS. That is the voltage. All the voltages are with respect to ground. So this is the gate source voltage. When it is high, the MOSFET is turned on, and when it's low, the MOSFET is off. And the next waveform is drain source voltage. That is the MOSFET drain source voltage, and the diode current here. And this is the MOSFET current. MOSFET M1, ID is the drain current of the MOSFET M1, same as the MOSFET current. And this waveform shows the power dissipated in the MOSFET. The power dissipated is voltage multiplied by the MOSFET current, VDS multiplied by ID M1. I just explained to you how to get this power waveform. Take any one of this waveform, ID M1 or VDS. I start with ID M1 here. Right click. In the expression, you add multiply ID M1 by, this is the voltage waveform, VDS. So this gives the instantaneous power. Okay, so now you're getting the same waveform as shown here. And I'm going back to the old waveform now. I delete this, whatever added. Okay, fine. So now we go into the detail about how to measure the losses in the switch. So this is the rising edge of VGS, is the turn on is happening at this edge, and at falling edge turn off is happening. So there is a power spike, power dissipation spike at the rising edge and also at the falling edge because of the turn on process and turn off process losses. So now we'll expand these edges and find out the losses during turn on and turn off process. Okay, I'm expanding here. I'll just cover the turn on process interval. Okay, fine. So this is the interval at which the turn on process is complete. So now you hold the cursor on this label, keep pressing Control key, press left enter key. You get these informations. Start interval, that is the start of the turn on process, and the interval end is the end of the turn on process. The average power dissipated during this interval, and this is the energy dissipated during this interval, that is 49.725 microjoules. If you multiply this with the switching frequency, you'll get turn on losses. I'll close this. I'll go to turn off process. I'm again running the simulation. Okay. So we saw the losses here, and now I expand the turn off period. Slightly increase this beyond it. Okay. I think turn off start here and nearly ends here. Okay, this is the turn off interval. Then again hold the cursor on the label here, press Control key and left enter. This is the start interval of the turn off process. This is the interval end of the turn off process here, average power dissipation, and this is the energy dissipated during the turn off process, that is 64.084 microjoules. Multiply this by switching frequency to get the turn off losses. That's about it. Close it. Again, run the simulation. Now we found out the turn on losses and turn off losses, and one more important loss is the conduction losses during the switch is on. When the switch is off, the losses will be negligible, so need not be measured. Now we'll measure the losses when the switch is on. I'll expand this area. Okay, so I want interval starting after the turn on process over, before the turn off process start. So I'll start so here I'm not able to get exactly this time interval, so I'm using cursors to get this interval. So I hold this on the label, then I right click, and then this attached cursor, none selected now. I select two cursors because I want to see the starting and the end interval. Okay, so there are two cursors here. This is cursor 1. I'll bring it to the interval start, that is the turn on interval start, on interval start, sorry. This is cursor 2. This is I keep it at the end of the on interval. Okay. Okay, so here the small window shows cursor 1 time and the losses, and then cursor 2 time and losses. So the on interval starts at this time and end at this time. Okay, So now what I'm going to do is I'm changing the x-axis to making this a starting interval and this is the end interval. So I right click here. Okay, that is I'm going to enter this number here, 40.085549. Okay, 40.085549. Okay, so the same way, this is the cursor to time. There is a end of on period, that is 42.013873. 3873. Okay, there are two dots. 42.013873. Okay, both are fine. I press OK here. Now the interval shown is just the on time. But since this y-axis is too high and the waveform is we are not able to see exactly the dissipation waveform. So I am changing this by right clicking at this point here, and then I'll start with, always power is positive, so I can just start with some 0.2 watts. Okay, this is the scale, and this put some, let me put some 40 watts. Okay, so now we can see this waveform around, start with around 20 watts and at the end about maybe some 30 watts or so. Because the current is increasing during this on interval, the losses the end of the on interval is more than the beginning. Okay, so now again we do the same thing. Hold the cursor here, hold the control key, and click left mouse. So this is starting of the interval. It's same as the cursor 1. This is the end of the interval, same as cursor 2. And average power dissipated and the energy dissipated during the on interval, that is 42.86 microjoules. Multiply this with switching frequency to get the conduction loss of the MOSFET. Let me close this. Okay. Again, run the simulation. Okay. Okay. So I would like to show you one more thing. By changing this diode, now I consider an ideal diode. If we use actual diode, there will be a reverse recovery. When the switch is turned on, the current in the diode is transferred to the MOSFET. So while all the current going through the load will be transferred to the MOSFET, and further there will be a spike in the current because of the reverse recovery of the diode. I would like to show that, and we can see that the spike during on process, turn on, when switch turn on process, will be more than what you see now. Let me change the diode. I right click here, pick a new diode, go for a 600 volt diode. It has to be fast recovery diode, otherwise the loss will be much higher. You can try a slow recovery diode and you can check the losses will be higher. I have taken fast recovery. 130 amps. Okay, I'm doing this 600 volts, 15 amps diode, and I'll run this simulation again. Okay, so now we can see the diode current. And you can see that the MOSFET current, there is a spike here. And you can see that turn on losses are higher than the turn off losses. Earlier it was the other way. To show the ID one, I just delete for the time being. You can see that reverse recovery current of the diode that has to flow into the switch. That leads to a forward current in the MOSFET, which resulted in a bigger spike in the turn off losses. Okay, with this I end the presentation on how to measure the switch losses in the LTspice simulation. Thank you.